Okay, today we're going to talk about capacitances. Capacitances are devices that can store energy. They can store electrical energy. Now, let me mention another. They both store electrical energy. So the question is, what's the difference between these two guys? Okay, this guy stores electrical energy, this guy stores electrical energy as well. The difference is the following. This guy releases his energy very slowly. So if you want energy released, let's say a battery, you guys all have used batteries and devices like calculators, remote controlled and all that kind of stuff. This guy will release his energy over hours and days. Okay. This guy can very fast, milliseconds and even nano. Okay. So what you do is, so oftentimes in a lot of applications, what you'll see is energies from store energy in the battery is transferred to the capacitor, and then it's released extremely fast for whatever application that you're doing. Yeah. So for instance, here's a typical application. So here's a circuit. Oops, let me, what I'll do is, okay. So here's a circuit. This is a flash bulb circuit. So what this shows you is when you close the switch, what will happen is the capacitor will get charged. Okay. What that means is energy is transferred from the battery to the capacitor. Okay. So now you've stored energy in a device where you can release the energy very fast. And then once energy is stored in the capacitor, what you can do is if you open the switch, energy is stored in this capacitor. Now you close this switch, and this energy stored in the capacitor will be discharged through this device. And this will be, so if it's a flash camera circuit, this will be a flash bulb. And so this energy is discharged very fast through this flash bulb, and this bulb will shine bright, and it'll turn night into day in a small area. Okay, like in a room, and you can take pictures at night. Okay, so that's the idea. So you transfer energy from a slow releasing device to a device where the energy can be stored. The energy can be released very fast. Okay, so that's a capacitor. All right, so now that we know what a capacitor is, let's get into the slides. So again, this chapter is about capacitance. We'll define the capacitance. We'll define capacitance. Capacitance can be given in terms of geometrical properties for certain geometries. Okay, and we'll do that. And then we'll look at how do we combine capacitors to get other capacitors and so on. We'll talk about energy stored in a capacitor. And dielectrics are insulators, and we'll talk about them. So those are some of the topics we'll cover. So here are some uses for capacitors. They're used in tuning circuits. Okay. So actually, let me go ahead and show you a tuning circuit. We'll talk about these circuits more in a couple of chapters. So we'll have to first introduce inductors. But so here's an inductor. And so here's an ideal tuning circuit. Okay. So this is a capacitor, this is an inductor. And inductors are inductance is denoted by L, capacitance by C. Okay. So okay, so this circuit here will oscillate with a frequency of 1 over root of LC. That's the natural frequency of oscillation of this circuit. Just like you have seen a mass attached to a spring, and this will oscillate, and the frequency of oscillation of this thing is 1 over 2 pi times k over m. So that's the natural frequency of oscillation of that device, of a mass attached to a spring on a frictionless surface. Just like that, this guy will oscillate, has a natural frequency of oscillation, 1 over, omega is 1 over square root of LC. Okay. So now, what will happen is if you're in a room with a whole bunch of frequencies, if you stick out antennas like that, a frequency that matches the natural frequency of the circuit, this frequency will set up via resonance, will set up a current, and that's how this is your tuning circuit. That's how your tuning circuit picks up this signal. Okay, so a capacitor is used in a tuning circuit. So that's what we're saying. Is used to tune receivers. Capacitors are used in tuning circuits as filters and power supplies and energy storing devices. Okay, so those are some of the uses of capacitors. Capacitors can store electrical energy just like batteries, except that capacitors can discharge their energy very fast, and that's the largest application that we'll see. So in this circuit that we saw previously, so again, when you close the switch, you can transfer energy from here to the capacitor, store energy in the battery, open this circuit, and then you can discharge this capacitor through this device. This could also be a defibrillator, I guess, or anything like that, where you're trying to jumpstart somebody's heart. Okay, so so those are some of the uses that we'll see for capacitors. All right, so so this is showing you showing you the numbers of a flash bulb circuit. So energy stored in a capacitor is used to light flash bulbs. So you can typically, in a typical circuit, you can store about 20 joules of energy in the capacitor. So here's what you can do with 20 joules. And that's what that thing is showing you. So with 20 joules, of energy, here's what you could do. 200 joules per second. 20 kilowatt into 1 second. Okay, so here's what I've done. This is 20 into 10 to the 3 joules per second into 10 minus 3 seconds. So what we've done is the 10 10 to the 3 will cancel 10 minus 3, the second will cancel that. And that's, so that's equal to 20 joules. Okay. But what does this mean? This means this is 20 into 10 to the 3 watts into 1 millisecond. Okay, so this is 200 into 100 watts into 1 millisecond. Okay. So here's what you can do with 20 joules. You can light 200 100-watt bulbs for 1 millisecond. Okay, so that's what that means. So that's that's what a flash camera does. A flash bulb will do. It'll shine like 20 100-watt bulbs for a millisecond, and then you take your picture. Okay. All right, so what makes a capacitor? Any two pieces of metal make a capacitor. So you can take any two pieces of metal, and that can form a capacitor, and that device can store electrical energy. Of course, that's not what we do typically, but in principle, any two pieces of metal can be used to store energy. Okay, so when a capacitor is charged by connecting it to battery, charge of equal magnitude but opposite signs reside on the battery. The conductors are equipotential surfaces and so on. Okay, so let me show you how to charge a capacitor. All right, so here's a parallel plate capacitor. Okay, here's a battery. This is the switch. And what we'll do is we'll connect a 10-volt battery to the capacitor. Now we'll close the switch, and what happens is electrons flow from here to this this plate. These electrons repel these electrons, which get to the terminal, to the positive terminal of the battery. Now this plate is positively charged, and this plate is negatively charged, and you can see that's indicated by the electric field lines going from the positive to the negative plate. And what has happened is now we've taken energy from here and stored it in this capacitor. Okay? And you see this, if there's no dissipated, if this energy doesn't dissipate, then it can stay here forever. Okay? And now you can use this energy stored in this capacitor to do whatever it is that you wanted. So you saw that how you could use that to light a flash bulb. You could use it as a defibrillator and all that kind of stuff. Okay, and we'll show you a couple of applications toward the end where energy is stored in capacitors, and then this energy is discharged through, and this energy is used to fire lasers in used in fusion reactions. Okay. So we'll look at that later. But anyway, so that's what we've done. We've charged this capacitor, and it turns out that the charge resides on the inner surface. Okay, so the inner surface is positive and this is negative. So let me draw a larger diagram of that. So when you charge, okay, so when a plate is charged, so here's a blown up view of a parallel plate capacitor. Okay, so the charge resides on the inner face, okay, on the surface of the conductors of this parallel plate conductor. And there's the electric field. Okay, so when a capacitor is charged, energy is stored in it. All right, so you saw how a capacitor is charged. Okay, the capacitance of a capacitor. So the capacitance of capacitor measures how much charge it can store per unit volt. Okay. So the more charge it can store, the larger its capacitance. And here's, in this diagram, you can see for a parallel plate capacitor, the charge resides on the inner surface of the plate. Okay. The units for capacitance are coulombs per volt, and that combination of unit is called a farad, after Mr. Farad, who studied these devices. A farad is a very large capacitance. 1 farad is very large. So in most microelectronic circuits and stuff like that, or in a lot of labs, we use microfarads, a millionth of a farad, or picofarads, a trillionth of a farad. Okay. So anyway. So capacitance are measured in farads. Right, so here are some electrical symbols. This is the symbol for a wire, for a capacitor. This is the symbol for a resistor, an inductor, a switch, galvanometer, it says all-time ammeter, a voltmeter, an ammeter, a battery, and often we don't write these plus and negative signs. So you just want to remember that the longer line represents the positive terminal, and the shorter one, the negative terminal. And here's an AC source. All right, so here's a flash bulb circuit that I showed you. All right, so here's the battery, and there's the capacitor. When you close the switch, the capacitor gets charged. And once the capacitor is charged, you can discharge the capacitor through your device. In this case, the flash bulb. Okay. So in your flash camera, all this is done automatically. When after you take a picture, you see the orange light blinking, amber light blinking. And what's happening is after you've taken the picture, you open the switch, the camera circuit automatically closes this switch and is charging the capacitor. And the amber light is blinking while the capacitor is charging. And if you took another flash picture when the light was blinking, you would not have a full charge, and the flash bulb, if it fired, wouldn't be as bright. Okay. So when the amber light is blinking, this switch is closed and the capacitor is charging. Okay. Now, when the capacitor is charging, charge flow into the capacitor plate till the potential difference equals the terminal voltage of the battery. So till what time does charge flow? Till the voltage across this is equal to the voltage across the battery. So let me. When you close the switch, charge flow into the capacitor till the voltage across equals 10 volts. Once the voltage across the capacitance equals 10 volts, then the charge flow stops. All right, here's a parallel plate capacitor. So the capacitance of any two conductors, is given by this equation. How much charge can it hold for a given voltage? Okay. So that can be measured. But if your two conductors have nice geometry, so for instance, if you have two parallel plates and they're opposite to each other, then the capacitance of this device can be given in terms of the geometry. And so for a parallel plate capacitor, it's equal to epsilon naught, the permittivity of free space, times the area of the plate, divided by the distance between the plate. So for the parallel plate capacitors here's the capacitance given in terms of the geometry. Okay. For a coaxial cable, a coaxial cable is something like this. Okay. So this has a capacitance associated with it. So for a length of this cable of length L, the capacitance is given by L times 2 times the Coulomb's constant times natural log of the radius of the outer conductor to the radius of the inner conductor. Okay? Natural log of B over A. So here's a spherical conductor inside a hollow spherical conductor. B is the inner radius of the outer sphere, and A is the radius of the inner sphere. Okay, so the capacitance is given by that. Now, in this for this expression, what you can do is you can try and make B large. Okay, as B goes to infinity, this expression will reduce to just A over KE, Coulomb's constant, or 4 pi epsilon naught A. So for a single sphere, for a spherical conductor, the capacitance of a single sphere is 4 pi epsilon naught A. Okay, and whereas the other conductor is assumed to be at infinity. All right, I'm going to pause now. Now is a good time to pause and give you guys a chance to ask questions.